Okay, everyone, so this is midterm 2 walkthrough, just going through the questions and answers for second one. So first question is a large molecule where we're asked to identify key components. First one, we're asked to put an asterisk next to each part of the amide bond, or an amide functional group. Now remember, an amide specifically is a carbonyl, some type of carbon constituent on this side, we usually designate as an R, and a nitrogen. You do not need necessarily to have carbons attaching over here. These are the designation be primary or secondary amide, because these could be also hydrogen at those ones. But most important is you have to have this part, nitrogen, carbon, oxygen, and a carbon in this position over here. So amide in specific is this nitrogen, carbonyl carbon, the oxygen, and a carbon on the other side. That's minimum. This is not an amide, that is a urea. That's because we have a nitrogen, oxygen, a carbon, and a nitrogen on the other side. So triangle goes next to each asymmetric center in the molecule. So here there are three. There's one here. This has an R or S notation. This one as well. This one. This is not a RS center, even though it has a wedge and dash. This is just showing geometry. Remember, there's three methyl groups. They have the same CIP priority, so they cannot be assigned as R or S. And then circle the most acidic hydrogen in the molecule. That is simply this OH, this carboxylic acid. It's not these NHs or any other molecule or any other part of this molecule. Okay, next we're asked to rank these in terms of the carbonyls being fastest, giving a 1, and slowest, giving a 5. And this is relative to the nucleophilic acyl substitution. Basically, if this anion, this good nucleophile, was going to attack these, which one would be fastest? Remember, this is basically a measurement not of how good a leaving group is, but how electropolarized the carbonyl is. So the winner is going to be this one. This is going to be our carboxylic acid. Not only do we have electron withdrawing groups, that is definitely the most electropositive group of the series. Number 2 is going to be our anhydride. So it doesn't matter which one you specify, but this one here is going to have good electron withdrawing group across this one. Not quite as good as the chloride because we have a little bit of oxygen donation by resonance that's helping to satisfy that charge. Number 3, your choice is between the nitrogen and the sulfur. So this really comes down to how electronegative the atom is rather than which one is a better leaving group. Either way, in this case, the sulfur is going to be number 3. It's less electronegative than the nitrogen, which gives you number 4. The lowest on the list is this OK. Remember, this is ionized. This is effectively oxygen minus. This is not electrophilic at all. We can't do substitution on these kinds of centers. So this is number 5. Okay, in the next one, we're asked to provide conditions in order to do an alkylation. Here we have a carbonyl, a ketone, and we have the more substituted center and the least substituted center. If you look at what we're trying to do, we're trying to add a methyl to this least substituted center to give you this. These are effectively kinetic conditions. So these would be low temperature, strong base, something like LDA, minus 78 degrees C. The next one, we're adding a methyl group to the more substituted center. That's this one. So that's effectively our thermodynamic. That's sodium hydride at something like 25 degrees C, warmer temperatures, because we're getting the thermodynamic enolate under those conditions. Now, as we're moving through this, what we're trying to do is indicate which atoms would allow us to do certain kinds of reactions. In this one, we want to indicate which ones will undergo alkylation if treated with an appropriate base and alkyl halide. So what we're really saying is which ones of these could possibly make an enolate that then could be alkylated. So A can definitely make an enolate. We have alpha protons that are available. C, also possible. Again, alpha protons that can be deprotonated. D is also possible. We have an alpha proton here that could be, and E, also possible, alpha protons. No alpha protons here, no alpha protons here. So it's simply A, C, D, and E. For the next one, which of these molecules cannot be used as a donor, which means as a nucleophile in aldol type reactions. Really, that's the opposite of what we talked about in the previous one. If you can alkylate it, that means you can make an enolate. These ones are obligate acceptors. B can only be an acceptor, as is F. It's only an acceptor. These cannot be used as donors, which also means they cannot be used to make enolates. Finally, if we're going to use the above molecules and we want to make this product, that's what we're doing, is we're bringing together two pieces. So in this case, this is an aldol condensation. Notice the conditions. We're treating it with base in methanol, and then we're following it up with acid and heat to make sure we push the condensation reaction. So this is an aldol coupled to a condensation. Now in the condensation reaction, that's the bond that we're breaking. We used to have a carbonyl at this center, and we're going to have a nucleophile at this center. If you look at that out, what this is a dimerization, in fact. So this green center here, if I was to disconnect it, that goes back to being a carbonyl, and given the substitution pattern that's present, we actually have something that would probably look like this, which corresponds to compound E. That's the acceptor. The acceptor is the electrophile in that pair, so that's this part here. The nucleophile is the donor. That's going to be this piece over here, and if you look, that's that same thing. Really, that's just this compound right here. Once again, it's a dimerization of E with E, both as a donor and the acceptor. All right, into reaction conditions. Now, to do this reaction, you notice there's two things that we're actually changing across here. We're losing this carbonyl, that's gone, and we're leaving the amide in place, or the amine in place. And this nitrile is still a nitrogen, except what we've really done is we've added a whole bunch of hydrogens, right? So this is a reduction reaction. Now, to take a amide like this down to simply the amine, that is our typical lithium aluminum hydride conditions. Those are also the same conditions we're going to apply to this nitrile. That's all you should specify. If you do choose to provide both conditions, two steps, first we're going to do the reduction with lithium aluminum hydride. After we do the workup in this case is going to be acid and water, something like this. Most important, though, is to designate that these are two sequential steps, not all at the same time. So, for example, if you had just written like this is kind of saying that all of these are happening in one bucket at one time. You're mixing everything you see here, not sequentially, and that is incorrect. Putting them all down at the same time like that basically means that we're going to have acid and lithium aluminum hydride present at the exact same time, which would be dangerous and ineffective. For the next one, we're going to do a transformation from here to here. Now, important thing in this one is to look at what part of the molecule corresponds to our starting material. Now, if you notice, we have this tertiary butyl CH2 carbonyl that corresponds to tertiary butyl CH2 carbonyl. Even though we've got this fragment over here, that's actually not these specific atoms. This is where what we actually have to do is we're bringing in a nucleophile. Nucleophile will attack at this center. Remember, that's our favored center. This is similar to what we've done with mixed anhydride type components. So this is the most electrophilic center for nucleophilic addition because we have two flanking oxygen groups will shut down that carbonyl. So as long as the nucleophile comes in, we're going to bring in this nucleophile, cut off and lose this part of the group, which means the nucleophile is just that fragment. So that's just phenol as my nucleophile. It's not this one specifically, that's just fortuitous basically for the type of molecule. You could also use this in the presence of a sacrificial base such as pyridine, not exclusively necessary, but possible to help. Now, another thing to watch out here is we don't want to add other nucleophiles, so it's not a good idea to add things like methanol. It's not a good idea to add things like methoxide, not a good idea to add things like hydroxide. All of these will compete with your alcohol nucleophile, so usually you just want to keep to a non-nucleophilic base or just the molecule itself, just a simple alcohol. Now, in this transformation, we're going from an ester down to, if you notice this is a hemiacetal. This is still a reduction because we're going from a higher oxidation state where we have 3 carbon-oxygen bonds down to simply 2. And if you notice, that molecule as the hemiacetal is equivalent to something where we had an aldehyde at one end, and then 1, 2, 3, 4 carbons is 1, 2, 3, 4 carbons OH, like this. So if I had this molecule where I have a free alcohol on one side, aldehyde, it will tend to close spontaneously to give me my 5-membered ring in this point. So really what I'm saying is I have to somehow take my ester, reduce it to an aldehyde, and leave this alcohol present. So really what that is diisobutyl aluminum hydride, or dibal, at minus 78 degrees. That's going to give me my reduction. We're under workup conditions. Since we didn't say you specifically had to specify it, you don't have to indicate it, but under workup, that's where we're going to free up the aldehyde and also allow the formation of this hemiacetone. So in the next one, we're taking this molecule and stitching the two pieces together. If you notice again, starting material, this fragment here is this fragment over here. That center corresponds to this center. And what we're doing is we're bringing in this whole other piece right here, with that being my acceptor. So this is similar to an aldol reaction across aldol. So one way you could potentially do it is first treat this with sodium hydride at 25 degrees, something to make the enolate first, and then in step 2 we're bringing in the acceptor. In this case it would just be this simple aldehyde where we're providing heat. The purpose of that is to make sure we push the aldol condensation, not just the aldol addition. All right, and the last one, what we're asked to do is bring together these conditions. What we want to try and focus on is it's some type of condensation reaction. Now, if you're looking at your fragments that you're putting over here, how I would map these peats off is we've got a nucleophilic center here, which I'm going to correspond to that center over here, and then we have an electrophilic center right here, and we're going to do this in the presence of sodium methoxide in methanol, and then probably something like, again, we really want to force the aldol condensation, so mild acid and heat necessary in the second step. Now, if you look at what we're doing, I've designated those two centers just to kind of isolate them. So the green center is my acceptor, the purple center, pink center is my nucleophile, that's my donor, and then effectively carbons 1, 2, 3, 4, 5, and 6 make up carbons 1, 2, 3, 4, 5, and 6. So this is a Claisen reaction effectively. So what we're going to do is make the enolate at this center and do nucleophilic coupling. Now there was a note that mentioned, well, how is it possible that this geometry of this bond between 3 and 2, it starts out trans, but clearly it ends up cis here. This is actually a little bit of a difficult step, but this is actually a process that's happening. We actually use this reaction to make these kinds of fused structures across this point here. What's actually happening here, and again, it's not relevant for the particular marks here, we want to identify that the ring closure that we have is between these two centers. In fact, how this actually happens under these conditions, these molecules here, like something like methanol, if you notice, what we actually have is an alpha beta unsaturated system through this point over here. So you can actually get nucleophilic addition to that center. It makes an intermediate. Let me just draw out that point like this. Where pink center is right here, green center is right there, and let me just designate this red center is this red center right here. So under these conditions, it's possible to actually do an addition of a molecule of methanol or methoxide, and what you've done is effectively turn this into a single bond, just temporarily. Now, the molecule can't proceed forward from this one. What you get is a nucleophilic addition, which gets you this enolate structure. Obviously, you've interrupted aromaticity, but what can happen then is this is under an equilibrium condition. It can then eliminate this back out in that sort of pathway, and when that happens, if the geometry has rotated, you can actually isomerize this bond back as follows. Once again, let me designate centers. Green center is here, red center right there, and pink center right here. So this is how we can invert the geometry of this bond to make it into a syn geometry. Then from there, that nucleophilic addition after enolate formation here, or deprotonation, allows us to do a classic sort of Claisen reaction. Okay, in this next part, a starting material, and we're giving you conditions, and we're asking you to come up with the possible products. So here we've got thionyl chloride, and we've designated that we have an excess of it. Notice that we have an acid chloride formation possible here, so that's the first one you should identify. Remember, primary amides have a special relationship with this. This is actually our conditions where we can convert this to our isocyanate. This is where effectively we're going to be reducing or removing water from this to condense this back down. So we're actually doing two reactions at both of these two centers. Acid chloride formed over here from the reduction of water or removal of water, and on the other side we have our nitrile, that what we've done like this. In the next one, we're treating this molecule with sodium methoxide in methanol. Under these conditions, now notice that we have no alpha protons in between these centers. These are actually blocked with two fluorines. So this is not an enolate reaction. In fact, what we just have is two different esters on either side and a good nucleophile here in methanol. So this is effectively our trans-esterification. What we're doing is we're swapping one ester for another. Your choice was, do I attack methanol at this center, which is sterically blocked, versus this center? This is probably preferable because we just have a primary alcohol next to it. So as a result of that, we're going to not touch the fluorines. Those are just in between. Both carbonyls are just isolated. And then we have our T-butyl group over here and an O-methyl group on this side where we've done our trans-esterification. In our next one, we're doing nucleophilic addition where we have an excess of methyl magnesium bromide, and then a workup step where we're doing our acidification. Now, this is our nucleophiles, obviously are methyl minus. Now notice this is our very strong nucleophile, methyl magnesium bromide. If you check back in our lecture conditions, even though we have what could be 1,4 addition to this center or 1,2 addition, when we use a Grignard reagent or strong nucleophile like this, the 1,2 addition is actually preferable. If we do 1,2 addition, that's effectively like we're just doing addition to the ester itself. We're not touching the other bonds. The major product here we're going to expect is 2 additions of methyl group to that center, where we're removing this methanol as a result of that particular point. Now in the next conditions, we are taking sodium methoxide in the presence and then acid workup. Acid workup here is just a process to make sure we neutralize every part of it out. And when we do this, we only have alpha protons here. This is an obligate acceptor, and this is for our Claisen type reagents. So we're going to make a nucleophile here, that's our donor. The acceptor is over here, so we're going to have a new bond between those two centers. Our aromatic group sits here, carbonyl, the new bond we just formed, and then our donor. Now, nucleophile is going to sit here, and the electrophilic center, acceptor, is there. So the new bond is between those two centers. One quick comment that came up was this is acid workup. Now, generally, this is just enough protons in order to satisfy, because you remember, after the nucleophilic addition, before workup, there's a very acidic group in between the two. So we're going to be sitting as something like this. And the acid workup's job is really only to protonate that center there. So with a mild acid treatment and workup, you do not have to do hydrolysis over here. That's not going to be a stronger case of sort of something like saponification. Normally, if we were going to follow this up with saponification, we use strong base plus heat to cut this off as a carboxylic acid and then eventually decarboxylate it. But this is just your workup to knock out that charge. Now, in this case, we're treating this with sodium hydroxide at 0 degrees in DMSO. Now, we have a couple of different choices of where we deprotonate. And if you notice, this molecule is symmetric top and bottom, so I'm only going to do the decomposition assuming that the donor is going to be from one thing up here, making the acceptor this carbonyl down here. What we're doing is an intramolecular reaction where if I deprotonated here, that would be where I have my enolate. The enolate can add to 1, 2, 3 carbons. That's probably too tight, so it's not going to form across there, so that one's out. However, if I make deprotonating over here, and this is my acceptor, I now have 1, 2, 3, 4, 5-membered ring. We're counting on the other side. We have 1, 2, 3, 4, also 5. So we have, depending on the carbon count, we have 2 5-membered rings linked between these two centers effectively. And if I'm doing this where I'm actually specifying low temperature, I'm trying to stop the reaction where I'm not allowing it to undergo condensation. That's the purpose of that specific condition. So we have a 5-5 ring where I'm going to designate, that's my pink center, there's my green, which means I'm going to have a carbonyl adjacent to it, where I'm numbering this off as 1, 2, 3, 4, 5, and then going the other way, 1, 2, 3, 4, 5, like this. Oops, sorry. So the last thing is carbon 5. I've just done this addition. This is going to remain after workup as the alcohol, because we haven't done a condensation reaction. We haven't eliminated that last water. Now in this next section, what we're doing is we're asked to evaluate an equilibrium and provide which side of the equilibrium is favored based on the stability or whatever the property we can look at to give us starting material or product favorability based on structure, charge, something like that. So in the first case, the major thing we're evaluating is we have an oxygen anion here versus an oxygen anion here. Remember, this is O- and O-. So we're really asked which of those two is more stable. And the stability here lies in favor of that one. So it's going to lie this way because the oxygen minus we have there will be stabilized by resonance. In the second case, we have a carboxylic acid on this side, and we have an alcohol on that side where we have ester and anhydride. Now, this is a normal reaction that you guys have been exposed to. We know anhydrides plus alcohols very, very favorably. These are really good electrophiles. These are pretty good nucleophiles. We should expect reactivity where they're going to move in this direction. The other way we can count that too is which one is a stronger acid. So in this case, the carboxylic acid we form on this side here is, if I was going to deprotonate them, let's say, right, basically if I had this guy versus this guy, remember, of these two, that anion will be more stable. So in other words, if I was going to nucleophilically attack this, the leaving group I'm just forming to go this direction is pretty good, pretty favorable. If we go the other way, if this was my nucleophile and I'm trying to actually attack this to cut out that leaving group, that one is a very bad leaving group. So reactivity principles help us here. Alcohol plus much more powerful electrophile, but also you can look at it in terms of the relative leaving group efficiencies as well too. Now, for this one, what we're asked to do is look at our species, and yes, you have two charged species over here, but what's the relative pKa's? So on this side, this molecule is my acidic species, this is my conjugate base as a result of that. If you remember, the relative pKa of something like these is about 10. Now, on the other side, this would be my base. That means what's I'm doing potentially here, this is actually my acidic species. So really what I'm doing is evaluating a relative acid-base equilibrium between these two. Now, if you go back, the anion we form over here, this anion that we're making is actually very highly stabilized because of the very powerful electron withdrawing group, this nitro. This is what we start to introduce. We talked about aromatic substitution reactions. So this anion minus is actually a very stabilized one. Turns out these protons, if you go back to your table, these protons have a pKa about 8.5. So pKa 10 versus pK 8.5. This is a stronger acid and will push the equilibrium in that direction. So this is a stronger base, stronger acid, equilibrium goes in that direction. Now this is your classic tautomerization. What we're talking about is an enol form here versus the keto form. As we mentioned before, generally the keto form would win. However, aromaticity gives you a really big bump. The phenol is going to win on that side. This last one, this was actually in previous midterms as well. What we have here is a stabilized enolate in this case. So this is a carbanion which is stabilized over here. However, this anion that we generate, this is via a Michael addition or conjugate addition, forms an anion which is very highly stabilized with this nitrile. This is a very good conjugate addition one, and also remember, just like the reactivity principles we talked before, this enolate is going to be relatively less stabilized compared to the nitrile, which gives you good pi delocalization. You could also look at this in terms of the relative pKa. The protons alpha to a nitrile are more acidic than the protons alpha to a carbonyl. So the mechanism goes this way. Once again, this was also on the sample midterm from last year as well. So for this section, we're asked to go through and provide the simple structures after each transformation. So starting from a carboxylic acid with diazomethane, remember these are our methylation conditions with diazomethane. That's where we're using the carboxylate as my nucleophile. So it's going to be the same structure we started off with, except O-methyl at that step. Taking this ester and treating it with ethanol under acid and heat. Really, under acidic conditions like this, we're not making enolates. Instead, this is our acid-catalyzed transesterification. This is where we're swapping out the methyl group for the ethyl group. Finally, what we're doing is we're treating this with an amide, or a methylamine, and heat. So that becomes our nucleophile. This becomes our leaving group. So all we're doing here is we're transforming that center, and again, since we're just going in with a neutral nucleophile with heat, we're changing this to the methylamine product across this one. So this is an amide where we're doing transamination. The second question, this is our sequence. We're doing sequential alkylation, treating it with base in methanol. Remember, we're matching that according to the ester that we have here. And then we're coming in with a electrophile. So that's where we have our nucleophilic center in the middle, electrophilic center just based on this alkyl halide. So we're adding this 3-carbon unit. So this is where we do our addition to make our O-methyl. And next, we're adding our 3-carbon fragment onto there like this. In our next step, we take this molecule, we treat it with base again, and now another alkyl halide. This is where we have this center here. So once again, nucleophilic center is there. We're going to build up the carbon skeleton, alkylating a second time. At that point. So we're still going to have our methyl center, and now we're adding in our ethyl piece like that. So it's 1 carbon methyl and then 2 fragments over here. So it's 1, 2, 3, 4. It's 1, 2, 3, 4. We have methyls on those 2 sides. And then finally, we're treating it with acid and heat. So this is where what we're doing is we're specifically trying to saponify this center over here and then give it decarboxylation. So the first thing that's going to happen is we're going to lose temporarily this group to become a carboxylic acid, and eventually that whole group will be lost as CO2. So that gives us our final fragment where we've got this part, we've got the alkylation that we've added, plus the second alkyl fragment from the other. And again, I'm just drawing it out this way to kind of give you the same geometry as we started off with. This can be represented in a linear fragment as well. Most common thing that to get wrong here is just your counting. That's why I'm trying to do this from color coding to show you where the atoms come from. So in this fragment, we're starting off with a molecule. This would have come from a Gabriel synthesis where we have this nitrogen phthalimide attached. We're treating it with hydrazine. That hydrazine is going to break this into 2 fragments without touching any of the stereocenters. So we're going to still have the up CF3 over here, and then up, and it's got a CH2 and then NH2 over here. So that's the amine fragment, and then this is your aromatic fragment. This is where what we've done is open up this to give you your hydrazine equivalent. Now carrying this part forward, we take SOCl2, or this phosgene, effectively chlorine, carbon, chlorine onto this. And what we're going to do is stitch those 2 pieces onto this nucleophilic nitrogen center. This is what creates, this is our reagent that we use for creating an isocyanate. So we're going to have our 5-membered ring as previous, our CF3, and then over on this side, we're going to have our nitrogen and double bond carbon, double bond oxygen. That's response to these 2 pieces, are where those 2 are coming from. Both chlorines have been replaced to give you 2 bonds to the nitrogen. Now these isocyanates are very electrophilic right here. That's a delta positive in that middle carbon center. So when we bring in a nucleophile, this oxygen, this is where we make our carbamates from that fragment. So the 5-membered ring is going to stay in shape. We still have the CF3 present here. We still have this, and then our nitrogen. And what we're going to do is add an oxygen to that center. So that's our nucleophilic fragment. All of this comes from this fragment here. That carbon in the middle is this carbon in the middle over here, and then we have our nitrogen on the other side. And in this last one, we're treating this with ozone under reductive conditions. So what that's going to do is open up that double bond to give you a dialdehyde. I'll write this out linearly. So on one end, we're going to have our our ketone. Then we've got the backbone, and finally this here. To number those off, this carbon here is this carbon here, and we have 1, 2, 3, 4, 5, and 6. It's 1, 2, 3, 4, 5. And this is carbon 6 over here, where we have a methyl attaching to it. So that's our linear fragment. We're then treating this with catalytic base. In this case, we're trying to do an Aldol reaction. Now we have 2 possible centers we can do. I could deprotonate out here at this methyl. However, that would give you 1, 2, 3, 4, 5, 6, 7-member ring. Too big. It would be preferable not to form that. Or we can deprotonate here, and that's 1, 2, 3, 4, 5-member ring back to the center over here. Now again, I'm deprotonating alpha to the carbonyl from the ketone, not the aldehyde, because remember, if I have a choice, the aldehyde will act as the acceptor, where the ketone acts as the donor. So that means we have a 5-membered ring that we're forming like this, carbonyl, methyl, and what we've done is we've made this, so kind of counting those off again. If, let me just double check here. If this red center here was my nucleophilic center there, that's 1, 2, 3, 4, and 5. 5 being this aldehyde center here. Now, under its final conditions, we treat this with base and heat. That's how we're trying to push elimination. So that's where we can drop this in to make our double bond to close that back up to give us this compound. Now, this is our mechanism question. And what we're asked to do is come up with air pushing mechanism. The starting material is the only source of carbon you have, and that's the important part here. Many people identified correctly that, okay, well, this molecule is losing an acetate over here, and we're gaining an acetate over there. However, quite a few people did transformations where we brought in things like acid chlorides or something else in order to add this group, and that's not present. Basically, this guy here plus conditions is the only thing you need to make this product over here. So this is actually an intramolecular lactonization or transamination. So under these conditions, what we can do is potentially use something like weak acid. So I'm going to use a catalytic acid, and because we're in methanol, I'm going to draw this as methanol as my chain carrier. So it's just a protonated methanol to start off with. Now under those catalytic acid conditions, we're going to protonate this carbonyl, making it more electrophilic, and then this nucleophile can punch in. So by doing that, we're going to make a 1, 2, 3, 4, 5, 6-membered ring. I'm going to draw this like this, where we have a nitrogen out to a OH, that's the carbon, oxygen, and then dash bonds down like this. Out the other side is our isopropyl. Now after addition, we're going to have a protonated nitrogen center over here. So now we can regenerate our acid catalyst. That's where we take our solvent and we're going to pick off a proton. That proton then gives us a neutral compound, neutral tetrahedral intermediate. So we now have our bonded system like this, tetrahedral intermediate, nitrogen, hydrogen, and ring, such as that. Okay, now we need to continue this process forward. What we eventually want to do is transfer this carbon here, which is this carbon here, which is that carbon here, over to that product. That's effectively what we're doing overall. So we're not changing oxidation state, we're not changing other fragments. Oh, excuse me, there's also a methyl group still attaching to that center as well. So now that we've got the new nitrogen bond to the target carbon, we need to complete this ring scission. So we're going to take the acid that we just formed. So we've formed a molecule of protonated methanol by passing the proton back from the nitrogen, and we're going to use this because we have to effectively break this bond. So I'm going to pick up a proton over here, and that's going to give me protonation on the group I'm trying to eliminate. So now that I've got that one protonated, I'm going to push in with my nitrogen and break that bond to give me that free alcohol. So now I've got my alcohol freed out, and I now have my nitrogen under these conditions. You can draw it in this particular way, or again, you could draw the ring scission in. I'll show you what my product would be from this one, where I have this bonding positive here, and then we either have to do a proton transfer to get back to a neutral nitrogen, loss of a proton over here to get me back to something like this. The other option you could do at this one as well is we can push in with this oxygen and down here. Now that's just going to get me closer where we just have a protonated carbonyl where after those arrows, just deprotonation of this oxygen would give you your final product. Both of those would be acceptable. Now for this one, what we want to do is just the first step of this reaction mechanism. So this was actually based on a Piazza question. Somebody was just looking for a simple protonation of a carbonyl. So this is not a protonation necessarily, but it's still an acid-base reaction. All you're doing is a Lewis acid-base addition. This is the first step of the Diebel mechanism, where you're starting with a neutral aluminum complex and your lone pair on this oxygen. So that's all you have to do is simply do a Lewis acid-base coordination of your Diebel, like so, and finish your charges. So positive on oxygen, negative on your aluminum, and then that can be continuing forward for your reduction. That's all. Now for this one, we're going to continue with a reaction. Under these conditions, we're going to do arrow pushing mechanisms where we can use proton transfer, PT, to help out. So under these conditions, we're going to first treat this with base, so something like hydroxide or something on that condition. We're going to deprotonate this center to make our enolate. So the first thing we're going to do, once we've made that enolate, I'll draw it out like this for now, is look at the rest of the molecule and try to identify what might happen next. And again, I'm starting off with this one in particular. We do have this fragment over here, but just from strategy, if you look at this molecule where we're trying to go to in the end, if this center right here was where my nucleophile would come to, notice that I've got a conjugate addition set up over here. This is something that I could potentially add to that center over there. So I need some fragment where I've got this ketone where I'm making a bond potentially between that blue and that pink. So once again over here, this is my blue center, and then the double bond, that's my pink center. That means this fragment right here is actually just this fragment here. So then taking that as a reference point, the carbon that I'm attaching that to, this one right here, must be that center over here. So if that's the case, now you've got to try and find your other two fragments, right? So there's got to be a fragment to the left, fragment to the right, that helps me to designate these two pieces. So in this particular geometry here, what I'm missing is, you notice there's a 5-membered ring that's being formed across here. That might be possible if what I've done is taken this blue center, I'll show you eventually, is the nucleophilic blue center over there, and then that would make this one the pink center that we just did that geometry close on. So let's draw out that fragment next. Nucleophilic attack is coming in through here to give you a conjugate addition over that fragment. So in doing that, what I've just done is I've closed this 5-membered ring between my blue center and my purple center. I've got this fragment, this alkene fragment in the middle of the two, and then I've got this carbonyl over here. So once again, just designate it out, blue center through there, green center attaching to that purple center over here. Now notice when you do this addition, you're adding to that purple center. The purple center is already part of another 5-membered ring. So it looks like this. It's a spirocyclic center at that point. When we do that addition, what we've just done is slid up the charge to make this responsible enolate over here. So that's the first addition. Now we formed that, and again, what I'm trying to highlight is we've just formed this sort of eastern part of the ring over here that's now represented in this fragment over here. Okay, now from here, we're just simply, there's not really, if you go, you could potentially ring close if I tried to close across these two. across that, but that gives you a 1, 2, 3, 4-membered ring. It's not going to be favorable at that point. It also doesn't look like the product we're trying to generate. So this is where we're going to do a simple proton transfer, and we're just going to go back to a ketone. So redrawing the product we have so far, we have our carbonyl, first 5-membered ring over here with our alkene, and then second 5-membered ring over here with another carbonyl at that position. And again, labeling out centers. Oops. Pink center here, green center over there, and blue center over here. And again, I've designated those. So now, if you actually look at your product, what we really got to find is where the heck is this center over here? Now notice what we have is this 5-membered ring, and then in that point, that's actually what's represented right here. That's this point right there. That's that red center at that point. That gives us that tertiary alcohol, and it's set up at that point, which means this over here, this light green, is that one over there. So if I was to make an enolate at that point and do a ring closure across that one, that would give me our final product across here. So we just have to generate one more enolate at that light green center and then do an aldol addition closing off at that point. Okay, now for the bonus question. This is actually a synthesis of penicillin V for anybody who's interested. Now I'm just going to give you some of the fragments. Again, I'm not going to give you all the details, but a couple really important things to sort of focus on. If you look at the molecule you're making here, this fragment here actually corresponds to this part here. Notice that green center there is effectively an acetal. It's a nitrogen sulfur, or in this case, it's like, you know, if you had 2 oxygens. That green center, though, does correspond to an aldehyde oxidation state. More importantly, then we've got this acyl chloride fragment. That's this piece right here. So that acyl chloride could add to a nitrogen. That nitrogen is going to come in. This one here is actually just this nitrogen. The rest of that molecule is only involved in a Gabriel synthesis in order to install it, where that nitrogen is going to be attached to that red center. That's this one here. Now notice in the particular geometry, this bromine center here is now this one. So this is going to be an SN2 reaction where we're going to invert that chiral center in order to get to this product over here. Now how we've done this though, the center that I'm going to designate, that green one over here, is actually this center here. That's our aldehyde. So the aldehyde center is already present. We do not need to do oxidation adjustments. There's no need for PCC or any reduction in this molecule, just ring closures and attachments, which means this final fragment here is actually this one, where most importantly we have a tertiary butyl group. To get a tertiary butyl group and open up this point, remember, when we cut that off, that had better be done with acid conditions, not base. So remember, the way we specially cut off a T-butyl group is under acidic conditions. So most important thing to put things together over here. You're going to be bringing in this nitrogen to this center by way of a Gabriel reaction. Now once we've done the Gabriel synthesis of the amine, first thing you probably want to do is cut off those bonds. Remember, the way that we cut off that point, if I just opened up that first, I would get a molecule that might look like, let's say, this. And I'm just going to leave you guys with this to think about, because it's probably the #1 error people made. What do you think might go wrong if I took this molecule and I immediately treat it with NH2, NH2? There is a problem by putting those two pieces together. This guy here and one of the functional groups you have in this molecule are incompatible. They will actually react. So you cannot do a Gabriel reaction and then open it up with hydrazine. That will destroy this molecule. That's a major problem here. So you have to change the order of addition. And if you notice, there's a way of potentially effectively protecting it. So by changing the order of addition of what bonds you put where, in what order, you will be able to do this synthesis correctly. But I can tell you that, yes, you're going to need a Gabriel synthesis, but you do not do that deprotection immediately. You have to do something else first, and then you can follow up with this point. So that was the major error in this point. Otherwise, I've given you sort of the other fragments of where things come up. As I said, too, the other major one was deprotecting this T-butyl group. That was done under acidic conditions. Final thing as well, too, is just a lot of people thought about doing things like PCC or other adjustments of these two centers. That's not necessary. The green center that I have there is an aldehyde, and that's exactly the same oxidation you have in your